Welcome, everyone. Thank you for joining us. I am Wing-King Wong, MIT class of '84, founder and president of the MIT Chinese Alumni Group. I will moderate this webinar. The topic today is Architectural Robotics meet Sculpting Arts. We are pleased to present Dr. Zhao Ma, who is MIT class of 2017 with a Master of Engineering in Civil and Environmental Engineering and a Master of Architecture. Zhao defended his PhD in architecture from ETH Zurich, where he conducted cross-discipline research between architecture and computer science, shared between ETH Zurich and Disney Research. Zhao is now an architect, designer, and computer scientist based in Zurich. He is a researcher at ETH Zurich, where he focuses on optimization-based methods for computational robotic fabrication. Zhao seeks to bridge the fields of design, engineering, and computational fabrication through cross-disciplinary collaborations. He has received awards and patents across disciplines, including architecture, landscape, and computational design. Zhao will speak for about 20 minutes about the technology, then address questions from the audience that may include overcoming career and life challenges. You may start posting your questions in the Q&A box. You can also upvote questions you'd like to hear discussed. And now, here is Dr. Ma. Thank you.
Hello, everyone. The slides is okay, right? Okay. Good afternoon, good morning, good evening, ladies and gentlemen. Thank you for joining this webinar, Architectural Robotics meets Sculpting Arts. I would like first to thank the MIT Alumni Association and Chinese Alumni Group for this invitation and coordination. So just before this webinar, I checked my flight records of the past years and realized that I actually flight a lot in the past years. So I grew up in China and finished my undergrad in physics and industrial design, and then moved to the States, to MIT, studied architecture and civil engineering. And then a few years ago, I came here to Switzerland to join ETH Zurich and started a PhD in robotic fabrication and computer graphics. It seems I've been to many places and I've seen different parts of the world. And frankly speaking, they're quite different in many aspects. In architecture itself, I've seen metropolitan cities like New York. I've also seen solitudinous, isolated houses. I've seen ancient buildings in Gothic styles in Europe. And I've also seen the buildings built in modern times that features more organic shapes. However, when we appreciate these wonderful human creations, few of us will recognize how they were actually built. And if we look into it, the building and construction process are a bit messy and quite labor-intensive. For the non-standard modern ones, the process is even more complicated and cost a lot economically because of the non-standard panels and individual components. But looking through the history, many industries has already upgraded its manufacturing process with machines and robots. Taking the textile industry, for instance, it has replaced the thousands of workers with modern automated machines. And nowadays, only a few workers can observe hundreds of machines at the same time. And if you look around, many daily products small as a piece of chocolate, or as complex as a car, are all made by machines, more or less automatically. So the question here is it possible to produce or make a building in this way? Actually, architects never stop trying to experiment the idea of making architecture in the product approach, or which we call it modular construction. But the fact is, when we do this, the design side is very limited. The standardized modules do not fulfill the inner design of designers and architects to build those crazy or the organic shapes. Until around 15 years ago, with the material of robotics and control system, an ongoing trend emerged inside the field to digitalize the manufacturing process of these architectural components while still maintain the diversity of the design. And generally speaking, throughout these projects, research discovered that using robots for architectural constructions poses several special challenges. The first is the need of adaptive fabrication process to suit the individual unique components. There's also a need for processing complex geometries rather than single boxes and straight and flat sheets. And also, based on different projects, we also need to include several fabrication constraints, including material strengths, robot reaches, which limit how we materialize our design from computer screens to physical reality. So how should we respond to these challenges? One thing I've learned from the past experience is when there are multiple parties presented in front of you, always choose the hard one. So my personal response to these questions during my PhD time is the clay. For three properties it enjoys: the wide application across different scales, including arts and crafts and architecture; the difficulty to manipulate precisely by machines; and the sustainability property, which we mentioned and need a lot for carbon emission controls. So in a comparative manner, robotic milling has been widely used for manufacturing hard materials precisely, but it is usually not possible to mill soft water-based clay, as the spindle will push the material away and prevent to control the quality in a very high precision manner. So the question to ask here is it possible to combine the precision of the machine with the flexibility of human hand to create clay artifacts with fine details? And additionally, is it possible to embed the user's design intention directly into the fabrication process, rather than just copy milling a virtual product from the computer screen to the physical reality? And what these two questions are actually asking is to use robot as our hand and commanded by our mind. And yes, you may think this echoes the MIT motto, mens et manus, minds and hands. So technically interpreting it, we want to transfer the movements of human hands into robot motion by preserving the idea of human mind. And to achieve this, we need a proxy media that we can transfer the design information into the robot command. And two challenges here need to be managed. And first, we need to digitalize the sculpting process by abstracting certain factors that can represent the designer's expressions. And second, we need to carry these information to the robotic sculpting processes. So before we dive into the detail, let's look at the tools we set up. The fabrication tools include a universal robot, a standardized robot arm, with a customized end effector composing a 3D printed base and metal wire handle, and an Arduino-controlled customized turntable to enlarge the reachability of the robot. And for this tool, I imitated professional sculpting tools used by human sculptors and use a desktop wire bender to bend various replaceable shapes that can be attached to the tools. Okay, here is the whole design to fabrication pipeline overview. From the input models, I first decomposed the whole model into several patches and generate tool paths for each of them. These tool paths are then sent to the path planning framework to generate robot trajectories, which can be executed by our robot on the physical model per patch. And in the end, we'll get output model that physically realized in clay, implemented by implementing our design ideas and expressions through the sculpting process. And here I develop intuitive interactive environment or software for the decomposition process. The user can freely draw scribbles on the mesh like drawing on a piece of paper with the mouse. The software will then decompose the mesh in the background based on the strokes. The user can additionally further draw additional strokes to modify the shapes and patches interactively. After these patches are generated and decomposed, the toolpaths are generated on the patch level using algorithms in the background. The toolpaths contains a set of trajectory points, which each defines the tool's positions and orientations. But notice here that at this point, if we directly run these toolpaths on the robot, we will have these kind of collisions because the toolpath doesn't avoid collisions between the robots and materials. That's why we implement this path planning framework, which will build a mathematical problem or optimization problem to solve this issue. We optimize for the robot trajectories by evaluating the distance between the toolpath and the target surface. We also implemented constraint objectives to avoid joint collisions and joint angle limits. There are also some other objectives try to improve the quality of the final results. And I will see in the next video. And here is a demo of how the optimization take an initial shape, generated patches and toolpaths as input, and sequentially run over each patch to find the robot trajectories. We run the optimization or the path planning process for each patch individually and store the results separately to allow independent fabrication of different sub-areas of the model. And after the optimization, we execute the trajectories on the robot. This video here shows how well the fabrication process matches our optimization results. You can observe that the noses fell off during the fabrication process. And this actually thanks to the property of the clay. We can just reattach a piece of clay and resculpt it. This will be a huge disaster if we use a CNC milling on a piece of hard materials, as the whole piece will break apart and we need to start all over again. And here are some models I sculpted using the system. The eye demonstrates the success of sculpting the highly curved iris areas, which cannot be achieved without optimization method. Especially notice here, right, I only need to provide very simple toolpaths designed by the designers, and the optimization of the system will do all the dirty work behind, and the robot will fabricate those toolpaths. This is a live video showing the quality and the details of the fabrication results, showing the path results at this time. We also work on this 3D mobile spring, which is a truly 3D object and challenge the reachability of the robots and the whole system. Here, the robot arm runs in space in different positions and try to sculpt the whole thing in a piece. And additionally, to stress test the power of the design tool, I created different sculpting styles on the same model, where I explored various decomposition and toolpath generation strategies, aiming to transfer these design sculpting styles to the physical artifacts. And these styles are all generated from my design interface with ease. So at this point, it seems that the physical is quite stable on the technical aspect, but it feels that it is still a bit far from artistic expressions. I want the robot to be more expressive and dexterous. So I look into the paintings. Throughout histories, many famous paintings created by famous artists have different styles. The different styles created by the artist also identify these artists in return. For instance, the Vincent van Gogh have very short strokes that you can identify in many of his later paintings. So the idea is to implement these style paintings in 2D in the 3D work I created. And with a bit of extra efforts, I successfully extracted these styles as embedded them into the robotic sculpting system. With single style, multiple style, and a contrast between different depth and emphasis on the surface. Okay, let's zoom out a bit and look back to the architectural industries. To this point, this project hasn't touched the application in the architectural scale, but it builds up a computation system that do the hard work of generating adaptive robotic trajectories for complex geometries, considering several fabrication-related constraints of the project. And I believe that it can be easily extended and transferred into other applications, for which I named two here. The sculpting, the surface treatment of large-scale architecture components using the system detailing ability. And the second one is the replace of some of the molding material, since the clay is cheap and sustainable. And we care the environment more than any time in the history. And generally speaking, my long-term goal is to build different tools as a toolbox so that we can create a Swiss Army knife for architectural robotic fabrication. So last, I'd like to end my presentation with a quote from Steve Jobs once said in 2011 Apple product announcement, that technology alone is not enough. It is technology married with liberal arts, married with humanities, that yields us the results that make our heart sing. And thank you for listening. Hope you enjoyed the presentation. If you're interested, you can find more of me at my personal website, beyonddisciplines.com. Thank you very much.
Thank you, Zhao. Thank you, Zhao, for a wonderful presentation. And the first question is the decomposition needed to make the path planning problem easier to solve? Or is there another reason?
Good question. So this is more on the technical aspect, I guess. There's two reasons. One is yes, it says path planning because for mathematically speaking, we need to limit or restrain the scale of the mathematical problem in a solvable or in a meaningful time, right? We cannot make it to run so long for the organization. That's why we decompose into small patches as a divide and conquer mentality to solve small problems individually and combine them as a whole. But actually the main idea or the main decision that drives this move is the goal of allow more expressively designed patches for the different areas of the model. Because if you treat the whole surface as one piece, and that is not very easy to incorporate different sculpting strokes for the designers as a whole. Sometimes you want to draw in this area in this way, sometimes you want to draw the other area with other ways. If you do a whole piece, then this is user interactively, it's not very easy and not good to implement. That's why we try to allow the user have more freedom on different areas to do their own design. And that's the main reason to do the global decomposition.
So the second question is, could you please compare a little bit your method with 3D printing in terms of resolution, cost, and construction time?
Yes, this is also a good question. So as you can see, this is more of a subtractive process that different from the 3D printing additive process. Right? So additive process now have one big limitation is the speed and efficiency, especially if you cannot change the nozzle size of a 3D printing, then the printing time is always limited by this. So you have one resolution of the whole model, and then you print it with the nozzle you decided. If it's too small, you can have more details, but you cannot have very fast manufacturing process. And on the contrary, I have larger nozzles, and then you lose the details and quality. So this process, on the contrary, is as you can see, we use very simple tools, and with the computational algorithms, we can even achieve fine details with very large tools. So it speeds up, even compared to milling, it speeds up the manufacturing time in a very high, like a lot. And also it's reduced the cost of using those high-end milling baits, or you need a lot of power to driving those spindles. Here it's only just robot on move, and there's no additional energy put into it. That's why we can work on this kind of amorphous materials, soft, deformable, which cannot be like used and implemented on traditional milling process, because the spindle speed is really, let's say, 18,000 RPM, will always destroy the soft surface when you mill it.
So would your method fully replace the manual skills of a human sculptor? For example, can the current robot fully reproduce the quality as good or exceed the work of, say, Michelangelo?
That's the long-term goal. I wish I could, but actually, we're still far from reaching that goal. Because if you look at some of the sculpting videos, I watched several real sculptors sculpting things. Right, there's many process that they work with their hands or different type of tools to create a specific feature that they want. And for now, because we focus on this single problem, also because technically speaking, it's not able to just make such a big leap on the technical side to achieve whatever a human can achieve with their hand. It's so much different, and it's so much harder compared to, so much harder to implement in the technical aspect. That's why we limited this problem to only subtractive, using this tool called loop tools. And we focus on this problem. So once this is done, we may extend it to other tools, and little by little, yes, we may have a larger Swiss Army knife in the future. But frankly speaking, so far it's still not comparable with the artistic style or expressions that human hand can make.
Great. And are the sculpturing strokes, direction, and depth specified by the user or generated by the software?
There's a default one, but like assigned automatic, but user can change it. And the direction is totally defined by the users. It just like for the parties, user don't draw it, because if you draw many strokes, it's also tedious. So we have this process of user draw this a guidance direction, and so we have assigned different parameters on the borders or the directorate boundaries of the meshes, and then the software will generate. but the user can add additional strokes to re-guide the directions, and then the system will regenerate it. So it's very interactive and user-friendly interface for the design process.
Yeah, that goes to the next question. Can you alternate the robotic tools in the same project in order to obtain different thickness and textures?
I don't quite understand this.
There's some typos, that's why.
Yes, we can alter the tools.
Yeah.
Actually, at the beginning, we designed many, you can see in the slides, many different kinds of tools. Some are symmetric, some are asymmetric. And later we realized that actually the algorithms we developed can use one or two types of tools to achieve the effect of many different types of tools. So we first tried many manual experiments using the various tools. And this very tedious manual work, takes a lot of time. And then we developed this computational algorithm, which is also described in one of my papers, that you can use just one or two simple tools, just triangle shape or the circular shape. And then with the complex orientation and movement of the robots, you can use the different areas of the tools to sculpt in different level of details. So that's one of the best part I like in the project.
Thank you. Do you see an application of your technology in restoration, medicine, plastic surgery? Or that sculpturing?
I'm not sure what restoration medicine is, but plastic surgery, yes, but it needs, usually if you look at the robots in medical field, it's another story, right? These robots are either for educational purpose or industrialized jobs. So it's a huge, its trunk it doesn't have those like surgery robots have very fine and refined small tools. So I don't have a lot of knowledge in the medical part, but I think anything that you operate on human bodies, you should have special like mechanisms to prevent disasters that destroy the human bodies. But the methodology and the computational algorithms, I think, for certain applications, they definitely can be transferred. Yes.
Your background crosses many disciplines. How do you find your mentors and sponsors? And how do you work with them?
So this is a good question, right? I have to say it's a bit of luck, because sometimes you try to find you have this interest and you don't find many places that have a position or a mentor that's suitable for you. And then sometimes just by a chance of luck, you just met someone and then they just happen to offer this position, and your background and your skill just fit it, and you just joined. So it's very, I have to say that my experience is a very atypical case for many people. Also, a lot of coincidence and unexpected things happens during the last 10, 20 years. Yeah, starting from high school. So yeah, that's hard to say. But one thing I can say for sure is you need to be more active to look for it, to actively use different platforms, ask people, and try to search. So my personal experience is once you show this like this inner power of you really want to do this, and then there will be many people that are trying to help you once they see this driving force inside you.
Wonderful. Yeah. And what are some of the coincidences and accidents that come to your mind?
For example, like when I was in undergrad, at the beginning I studied physics. And then someday I realized that, so for people who are studying theoretical math and physics or those natural science, at some point you realize that at least to yourself, that you will reach certain level and then you cannot reach higher even.
Oh.
So yeah, I think at least to me is frankly speaking, this is the fact that I realize I can only, even no matter how hard I push, I can only reach a certain point. And then on the other side, I'm also interested in creating some kind of things rather than just discovering new laws and new rules of the nature. And then that's where I kind of switch a bit to a different industry, different disciplines. And then by some kind of combination of hard work and luck, I decided to apply for MIT and I got admitted. So these are all kind of luck and coincidence. And then at MIT, at the beginning, it was just architecture. And then through some of the courses, I realized, okay, I want to get more of the technology at this place. And then I applied for a different degree, which was also luckily accepted. And then I started dual degrees. And then later, something similar happened when I was applying for my doctoral degree. And that's why I coincidentally came to Switzerland.
Wow. What an amazing
answers
journey.
your question, yeah.
Yes. And that dovetails into the next question. You have education in so many areas. For an undergraduate starting college now with an interest in these areas, what should they study? So many disciplines are involved.
Yes, it's many disciplines are involved, but they contribute in different ways, I have to say. And if you mean specifically robotic fabrication in architectural disciplines, I think for bachelor's, for undergrads, I don't know which country are located, but a solid math and engineering backgrounds will help you a lot in your graduate life and PhD life. Because what I observe from around is for people who are doing this in this new kind of emerging field, the mathematics they know and they can master will, to a large extent, defines the depth they can reach in the research period. So that's why, this is because there's not many tools. We are developing tools, but there's not many tools available at the moment that are already easy to use. That means if you enter the disciplines in recent years, you are advancing these disciplines yourself, and also you need to develop tools for your own use or for the industries as you grow with the industry together. And with this requirement, you should have a more solid engineering background than most of the traditional architecture education in bachelors in many countries.
Thank you for the wonderful response. Okay, now we are back to technical questions. The next question, I do a lot of large scale, hectares to square kilometers in land size, master plans or city scale urban design, sometimes on site, I cannot physically visit, especially during this COVID pandemic period. Can your method provide accurate models of the site topography to facilitate my kind of work?
So the short answer, unfortunately, is no. And the long answer is I think we are talking about things in different scales. For I think the scales you are talking about is more like landscape and urban planning, right? So these are more of it's related to typographies, transportation, etc. more than this kind of what I'm doing as individual architectural components. So the larger components we made is relatively the scale you can transport by a truck on the road. Otherwise, you cannot move it to the side, right? So for the areas you mentioned, I think you can look into. I'm not expert, but what I can think of is you can look at. There's Google Earth. There's also a Google Earth engine as a tool for developers that you can explore different areas of the Earth, not in a fine resolution, but in a, as you said, in a hectare or square meter scale. And those scales, the experts in landscape and urban design will answer your question much better than I can. So I hope that will help.
Okay, the next question is, could you share views on larger scale application, again, larger scale, of robotics in architecture, pouring concrete, bricklaying, for example?
Yes, so I would say concrete pouring and concrete and bricks are quite different. So if you look at the projects, I mean, installation scale or large scale, we can say 3 types, right? One is assembly. So there's bricks, there's wood elements, which you produce single elements and then try to assemble it either stack it or in a very complex way. So concrete pouring and let's say clay is a different story because the material is kind of amorphous, and the material, when you work with it, it's soft and flow, and when it's hardening, it's cured, it's solid. So this has a different, I mean, inside or on the bottom level, have different logic for working with these 2 different types. For the assembly process, you care more about the assembly sequence, right? The collisions, how you place each element in different areas and how if the whole thing can stand, let's say. And for the concrete pouring on the clay, you care more about maintain the shape when the material is not able to stand on their own. And there's also other issues of either the material shrink or crack. There's also temperature controls, environment controls. You want to do it in a relatively stable environment temperature so that the curing process is stable. And the third one is not very typical. It's just a combination in some of the projects of combining these 2 methods as a whole project, or some kind of non-typical way like 3D printing. I would say it's not pouring concrete, it's also not bricklaying, because the layering process is layer by layer, but the material is amorphous material. And then the material is not cured as a whole, but it's cured layer by layer. So for this, you need to develop totally different approaches that's just suitable for these of technologies. Yeah, so you cannot just talk generally like applications for robotics in large scale. You need to, I mean, architecture has one aspect that computer science doesn't touch. It's the materialization and the material property, that we work with materials. And this is usually the hard part to predict or simulate in physical environment. You need to do tests rather than just coding in a virtual environment.
Okay. So in order to pursue your profession, you have to study and live in 3 different continents, China, North America, and Europe. How do you adjust?
In which aspect?
Every aspect, it would be very different, right? For all the different continents, like in education, in technology application, in job searching, in research searching.
I think culturally, it definitely is very different because like America is different from Europeans, and then in China, of course, the culture is very different from let's say the Western society. But I mean, from my own experience, and most of the time I stay in an academia environment. And then I have to say again that my experience is not very atypical because in China, my time of study, because the education resource is not abundant, so different schools always have this kind of selected class or a form that you reselect students from a large group, and then you put more resource on these students. You give better teachers, etc. Right? I was in this kind of class in elementary school, high school, even university, and then I came to MIT. So the environment in the world is very friendly. The professors are friendly. The classmates are friendly. They're open-minded. So in these aspects, I didn't experience a lot of difference between China and the States. But here, I think is for PhD is no matter, it's no longer the same type of environment, and there's some difference. And you work through it, you experience up and downs, and then you try to overcome it in your own way. So I think generally speaking, everyone have, let's say, a inner model of the physical world they interact with, right? And then this model is, at the beginning, is very different from the reality. And as you grow up, you experience things, and you refit this model little by little with the parameters you extracted from the realities. And this model will be more and more similar to the reality, and then you know how the world works more and better. And that's the process of grow up, I think.
How do you handle the ups and downs, especially the downs? And what are the downs, if I may ask?
Yeah, you may ask. So you know, like if you search in Google, right, there's a term called the valley of shit. Sorry to say that word, but the term is like, it's the valley of shit. So that during your PhD time, you experience this uninformed optimism, informed pessimism, and then valley of shit, and then informed optimism. So I think most of PhDs, unless you're super lucky and you're super strong and your advisor is super good, will help you through, you always experience this kind of downtime during our research. And of course you can quit, but if you don't, then you always need to find a way that you yourself can handle and know better to overcome it, and believe that there will be ups again in the future, right? Like life is never perfect. Life is always imperfect. So there's always up and downs. And then, yeah, life is like marathon. So don't be trapped in like shitty valleys in the short term. Just think about when we're in those areas, you just think about in the long term that things will get better. And then this gives you strength and courage to overcome it.
Thank you for great advice. Now we are back to technology again. The next question, since it is subtractive method, how can you avoid or minimize the breakage or damage of the piece? And what will be among the best material for art pieces? Is it plastic or wood?
So that's for the first question. That's the reason why we developed this this optimization. We formulated this optimization problem, like mathematically try to solve it, right? So at the first part of this project, we do a lot of manual tests, physical experiments. We manually or very tediously decide the position of the robots little by little and try to sculpt it. But as you can see in the eye model, the iris areas is always very, very hard to do. And also for the face model, the nose areas. If you try to do it point by point, part by part for the robot trajectory is such a tedious. Like just one day you just only do a small errors, and you still have clearance. So the algorithms is the tool to resolve all these, right? That's also why I say you should have a very strong math background and feel comfortable to use it, because then you can abstract a problem exists in the reality to math problems and use existing tools that developed by other scholars, right, to resolve this problem, these applicable problems. And then once you've done it, it's like amazing, because you can never imagine how good it works once you tune everything to the state that solve the problem. And for the second question, there's never a best material for art pieces. The arts, let's say, in general, is not like engineering, it's not like science. It's not evaluated quantitatively. So it's there's of course evaluation standard or rules to look at different art pieces, but it's never it's very hard to score it. And also for materials, for different purposes, for the expressions that artists want to embed, there's always different answers to different words and with different artists.
Thank you. The next question is from an architect and a sculptor. There are two questions here, so I'll ask the first one. The question is, having machine do the work requires everything to be designed beforehand. Creation is a discovery process. How do you interact with the creation?
Yes, that's also one of the reasons we developed these systems. As you can see in the decomposition part, also later, which I didn't show in the sculpting styles area. We try to, because if you want to use robots to do the sculpting process, right? At the moment, we didn't approach it in a human computer or human robot interaction method. So we ask the robot to do it totally. And then it's a question of how to embed this design idea or design process into, or embed these ideas into the fabrication process, so the robot can do whatever I want. That's where I, like my UI address, that we try to develop as easy to use as possible interface. You can just like drawing on 3D models or drawing on papers. You draw all those areas to decompose it and then later draw additional strokes to define the things you want. It may not be the final thing for everyone, but from what we experimented and surveyed with the colleagues, it's a quite easy to use software to do the things that we want to achieve in this project.
I noticed that in your answers, when you solve a problem, you show a lot of joy. What are the joyful part of your work? What do you enjoy the most?
So the most enjoyable part is, to me myself, is using technology improvements to achieve things in the artistic aspect. So it's similar to what like Steve Jobs once said. So technology itself, so if you only consider technology problems or application problems, sometimes you'll be trapped. You consider these short-term issues or small problems in the near run. But if you look at larger pictures or sometimes try to achieve, no matter the cost, no matter the effort, if you say, I just want to do this, I want to achieve this in an artistic way. And for this, you develop tools that may not be useful at the moment, but usually to achieve this higher goal, you develop tools and methods that will feature the technology improvements later. So the combination of the two sides actually are the most enjoyable parts in my work, I would say. That we use arts as a driving force to drive you to improve these technologies and later foster the improvements maybe in the field. Yeah.
Yeah, and you look at the long term.
Yep.
And someone here is interested in your future plan. Do you plan to pursue a career in teaching within a university, or would you go into the field of architectural practice?
This are you a recruiter? this
Give you a job.
this at the moment I'm not sure. Maybe not. I mean, what I can say is definitely not traditional architectural practice, because as you can see that traditional architecture and civil engineering is quite is a field that are not very sensitive to technology improvements and technology new technologies. So the current way of building things is costly, is not environmentally friendly, it's also very labor intense. And as you can see in other manufacturing industries, the change has been done in a very mature way, the automation process. And I would say this, I mean, my personal belief is this will be the next move for the architecture field. And yeah, so next step may be something related, but I may not give you a very detailed answer here at this moment.
Very diplomatic. So the next question is another technology question. I notice printing has to rely on usage of fluid or malleable clay, like materials which are applied as layers of slurry, which eventually build up and hardens into the form design. If I want to construct a final form in harder materials, say metals, do I need to turn raw metal material first into a molten form in order to print it?
Yeah, for metal printing, yes, of course. There's already commercialized and very fine-tuned research products that you print metals. You can also print biomaterials, etc. Like for metals itself, there's this kind of soldering, or I forgot the term, this process of melting metals first and then print it and solidify it. So you will see a very uneven texture once it's finished, because the melting and re-solidification process. And then in the industry, what I know is you do post-processing of the surface. You can mill it afterwards, or you can use other methods to make the surface more smooth. But the printing itself won't give you a very smooth surface because of the melting and re-solidification process. Yeah.
Okay. I have a comment from an audience, again, coming back to your joy. And she was thinking about a question she asked a musician about synthesizer, you know, machine versus creativity, human creativity. And she feels that apparently musicians and audience still relate more to humans. What do you think?
At the moment, maybe in the short term, yes. But I'm technology optimistic. So, for example, in the past, no one can think that robots can replace many of the work that human work, and they cannot. They can. I just saw yesterday news that the two robot arms make drinks in a bar. as like highlights of the above. So I think little by little also combined with the development in artificial intelligence and those computation improvements. That's how the society and technology improves, right? And then for the crown of human endeavors as musicians, artists, painters, etc., right? Like do those art stuff. And it might be still far from reaching to that stage. But yes, I believe and I hope that that's the driving force of why and how we push technology.
Wow. On that note, thank you so much for a very fascinating webinar. And thank you, Dr. Ma, and
Thank you,
everyone. The broadcast will be available on the MIT Alumni Association's YouTube channel. For the MIT community members, please join the MIT Chinese Alumni Group. You don't have to be Chinese to join us. And for the public members, please link in with me and message me to be added to our event invite list. Let us work together and empower one another for a better world. Dr. Zhao Ma, the MIT Chinese Alumni Group, and I thank you again for joining us, and we look forward to seeing you in the future. Until then, goodbye.
Thank you very much. Bye-bye.